Now, design of stringer beams. Design of stringer beams. Right? So we'll be designing our stringer beams. The first step in designing a stringer beam is to calculate the dead load due to self-weight of slab and the wearing cord. Step number 1, we have to calculate the dead load. Dead load due to self-weight of the slab, self-weight of slab and wearing cord or wearing course. All right, how much is that? That is 7 multiplied by 1.875. This 7 comes from, since we have earlier calculated the dead load due to the slab and the wearing cord, wherein we calculated the total dead load due to self-weight of the deck slab and the weight of wearing cords, that came equivalent to 7 kilonewton per meter square. So this is 7 and 1.87 is the spacing. You can see here, stringer beams, they are spaced 1.875 meters apart. So the dead load due to self-weight of slab and the wearing cord will be equivalent to 7 multiplied by 1.875, which by calculations is equal to 13.125 kilonewton per meter. All right, this is the dead load due to self-weight of slab and the wearing cord on the stringer beams that we are using in our steel truss bridge. All right, and this is the cross section of the deck, wherein we have stringer beams which are placed 1.875 meters apart. All right, and these are the truss details. 6 panels of 5 meter each, Warren truss. All right, so dead load due to self-weight of slab and wearing cord is equivalent to 13.125 kilonewton per meter. After that, we have to calculate the self-weight of stringer, because these beams have some self-weight. Self-weight of stringer, we are assuming it to be equal to 1 kilonewton per meter. Why? Because at this point, I don't know which section I am proposing for my stringer beam. So I am just assuming that self-weight of stringer be equal to 1 kilonewton per meter. All right. So total dead load on the stringer will be equal to total dead load on stringer. I'm designing my stringer beams and the total dead load on the stringer is equal to the summation of the two, 13.125 plus 1, that is equal to 14.125 kilonewton per meter. Please be mindful of the units. All right, 14.125 kilonewton per meter is the total dead load on stringer. 1 kilonewton per meter is its self-weight, which I am assuming, because at this point of time, I don't know what section I am proposing to be used for my stringer beams. And 13.125 kilonewton per meter is the dead load due to self-weight of the slab and the wearing cord on my deck slab. All right, that load will come on the stringer beam, and stringer beam has some self-weight as well. So the total dead load on the stringer beam is equal to 14.125 kilonewton per meter. Now I have to calculate my maximum bending moment and my maximum shear force due to this dead load on the stringer beams. All right, so let's calculate. All right, we rub it first. Now this is our stringer beam. This is 5 meter long because I'm proposing that I'm using 6 panels of 5 meters. All right. Now the total dead load on this stringer beam due to self weight of this deck slab and the wearing cord plus its own self weight is equal to how much did we calculate? 14.125 kilonewton per meter. Now this is a UDL on the stringer beam. This total dead load is a uniformly distributed load on my stringer beams, which are 5 meters long and are placed 1.875 meters apart. And now I have to calculate, and this is the dead load, please mind it. I have to calculate maximum bending moment and the maximum shear force because of this load onto my stringer beam. Now we know this is a simply supported beam, and when simply supported beam is subjected to a UDL or uniformly distributed load or its entire span, the maximum bending moment is in the shape of a parabola, and it's given by, we know it, how much? It is LWL square by 8. In this case, this W is 14.125, length is 5, square of 8 divided by 8, and this comes equal to 44.14 kilonewton meter. So this is my maximum bending moment on the stringer beam due to the dead load, which acts as a UDL of 14.125 kilonewton per meter. All right, and this is a simply supported beam. Please note this. Both cross girders as well as stringers, these are simply supported beams. All right. After that, we also know that maximum shear force in a simply supported beam that is subjected to a UDL along its entire span is given by WL by 2 W 14.125, length 5 divided by 2, that is equal to 35.31 kilonewtons. All right, so I calculated the maximum bending moment due to this dead load and the maximum shear force due to this dead load as well. Now I have to calculate the bending moment and shear force from the live load. All right, we know that the live load is, we have been asked that we have to design the steel truss bridge according to IRC class AA tracked vehicle. All right, and we know according to IRC class AA tracked vehicle, the live load is given as. Now, after that, I have calculated the maximum bending moment and the maximum shear force due to the dead load on this stringer beam. I'll be calculating the maximum bending moments and the shear force on these stringer beams by the live load. All right, the stringer is subjected to maximum bending moment. The stringer is subjected to maximum bending moment when one of the track is directly on the panel. All right, the stringer is subjected to the maximum bending moment when one of the track is directly on the panel. All right, this is the IRC class AA tracked vehicle. All right, and this is my panel, 5 meters long, 1.875 meters wide. All right, and the weight is 350 kilonewtons. Now I have to calculate the maximum bending moment and the maximum shear force on my stringer because of the live load. And let me make the diagram first. This is my stringer beam. It is 5 meters long. All right. Now I'm saying that the stringer is subjected to the maximum bending moment when one of the track is directly on the panel. This is my track and the weight is RC class AA tracked vehicle. So this will be 350 kilonewtons and this will be for a length of 3.6 meters. All right. So stringer is subjected to the maximum bending moment when one of the track is directly on the panel, and the diagram I have made, I have to calculate my maximum bending moment and the maximum shear force because of the live load that is coming on my stringer beams. And as already discussed during designing of the deck slab for the same bridge, A and B are the dimensions of the tire contact area in the longer and the shorter span, and we know that this is A, this much. A is 3.6 meters and B is how much? 0.85 meters. All right, these are the dimensions of the tire contact area in the long and in the short span. All right, so since the live load for this steel bridge is given that we have to design it as per the IRC class AA tracked vehicle, so this will be 350 kilonewton and the tire contact area in the long span is how much? It is 3.6 meters. So stringer is subjected to the maximum bending moment when one of the track is directly on the panel. So this is the track, 350 kilonewton. It is directly on the panel and the dimension of the tire contact area in the long span is given by 3.6 meters. Now this is my condition. And now I have to calculate the maximum bending moment and maximum shear force for this simply supported beam, which is under this type of loading. All right, so let's calculate this. All right, now maximum bending moment for this beam is given by, since this is 350 kilonewton, and please be mindful of the fact that this is not in the dimensions kilonewton per meter, otherwise the process of calculation would have been different. But this is, since a concentrated load which is acting over some distance is 3.6 meters. Now we have to calculate the maximum bending moment for this beam, and that is given by WL by 4, and then we'll subtract WA by 8. All right, so maximum bending moment will be given by, how much is W? 350. How much is the length? 5 divided by 4 minus W, 350. A, how much is A? It is 3.6 divided by 8. By calculations, my maximum bending moment is equal to 437.5 minus 157.5, and that is equal to 280 kilonewton meter. All right, so this is the maximum bending moment due to live load on my stringer beam, and we say that the stringer is subjected to maximum bending moment when one of the track is directly on the panel. So this was the condition, and I have calculated my maximum bending moment. Time to calculate the maximum shear force, and let's see when does the maximum shear force occur. The maximum shear force occurs when the track is along the left side of the panel. So let's draw the diagram for the beam. All right. Maximum shear force occurs when track is along left side of the panel, left side of the panel. Let's make the diagram. This is the stringer beam. All right. How much? 5 meters. So we're saying that the maximum shear force due to live load, please mind that these calculations are due to live load. Dead load we have calculated. All right, so maximum shear force due to live load occurs when track is along the left side of the panel. All right, so this is my track. This will be for a distance of how much? Tire contact area for IRC class AA tracked vehicle, 3.6 meters. How much is this? IRC class AA tracked vehicle, 350 kilonewton. All right, so now I have to calculate how much will be the remaining distance. If this is 5 and this is 3.6, the remaining distance will be, from this point to this point, it will be 5 minus 3.6 divided by 2. This is 3.2. All right, so the distance from here to here is how much? It is 3.2 meters. All right, so this is the stringer beam. Maximum shear force due to live load occurs when track is along left side of the panel. All right, so this is the tire contact area, 3.6 meters. This is 350 kilonewton because live load we are considering IRC class AA tracked vehicle. All right, tracked vehicle. These are the loading conditions. Now, if this is 5 meters, this is 3.6 meters, the distance from the center of this tire contact area to this point is equal to 3.2 meters. I've subtracted 3.6 divided by 2, half of the distance from the total distance. So this distance is 3.2 meters. All right. Now let's calculate the shear force. Let me call this distance as A dash. All right. So maximum shear force. Ultimately, our motto is to calculate the bending moments. All right. Due to both dead load and the live load. When we have the moments, then only we can design the sections. All right. What type of a section I'm using for my stringer beam. All right. So the first and the foremost criterion for everything is to calculate the moments, be it the deck slab, the stringer beams, or the cross girders. We did same in the case of deck slabs. We calculated the moments and then accordingly we saw what type of reinforcement extra we are going with. All right. In the same manner, during the design of stringer beams, we have to first calculate the moments. Moment is the ultimate criterion on which our design process is based, because we have to calculate what moments are going to be generated there. Then only we can design the sections. So in case of cross girders or stringers or deck slab, first and foremost step is to calculate the moments. Now moments in case of these stringer beams, or in case of the panel we designed for the deck slab, it's both due to dead load and due to live load. All right, dead load we are considering and live load is our IRC class AA tracked vehicle. And when we have moments, then only we can say or we can go on designing our sections. What type of sections will be capable enough of handling these moments? All right, so let's see how much is the shear force. Maximum shear force due to live load on the stringer beam occurs when the track is along the left side of the panel and is given by W A dash by L. How much is W? It's 350. How much is A dash? 3.2. And how much is the length? 5. By calculations, maximum shear force is 224 kilonewton. All right, so we have calculated the maximum bending moment due to dead load, the maximum shear force due to the dead load, the maximum bending moment due to live load, and the maximum shear force due to live load. All right, after that, what is the step? We have to apply the impact factors. All right, impact factors due to the live loads. There will be no continuity factors. Continuity factors we take during designing of deck slabs. All right, but not during designing of beams, be it stringer beams or be it the cross girders. All right, so now I have to apply the impact factors. So applying impact factor on bending moment and shear force. I'll be applying impact factor on bending moment and shear force. All right. And please be mindful that we are applying impact factors on bending moment and shear force only due to the live loads, not due to the dead loads. All right. So bending moment, how much did we calculate it? It was 280. My impact factor is 25%. So let's apply the impact factors. 1.25 multiplied by 280, it is equal to 350 kilonewton meter. And shear force, we calculated as 224. I'll be applying the impact factor. It is equal to 280 kilonewton. All right. So my bending moment due to the live load after applying the impact factor is 350 kilonewton meter, and so is my shear force after applying of impact factor due to live load is 280 kilonewton. All right, now total design moment. Total design moment for my stringer beam is bending moment due to dead load plus bending moment due to live load. All right. How much is my bending moment due to dead load? We calculated it. It was 44.14 kilonewton meter. And how much is my bending moment due to live load? After applying of impact factor, it is 350 kilonewton meter. So my design moment is 394.14, which is approximately equal to 395 kilonewton meter. And my design shear force is equal to design shear force. It is equal to, due to dead load, how much? It was 35.31 kilonewton plus due to live load after application of impact factors, it is 280. So by calculations, that is equal to 315.31 kilonewton, which I'll be approximately taking equal to 316 kilonewton. All right. So now I have my design moment. I have my design shear force. I'll be designing a section for my stringer beam. All right. For that, I have to take section modulus first. All right. Section modulus will give me what type of the section I am proposing to be used for the stringer beam for the steel truss bridge that we are designing for IRC Class A tracked vehicle loading. All right. Section modulus. How much is section modulus equal to? It is designated by Z. It is equal to M by sigma B, where M is the design moment and sigma B, this is the permissible bending stress in girders. Permissible bending stress in girders, be it stringers or cross girders. All right, and it is equal to 0.66 multiplied by the yield strength of the section that we are using. If you recall the question, it did say that, let me read it out for you, that materials you have to use is M25 grade concrete and Fe415 HYSD bars for deck slab. That is all, we have designed that. And it also said that rolled steel sections with an yield stress of 236 Newton per meter square you'll be using, conforming to IS 226 and IRC 24 are available for use. All right, so this is given in question itself, that rolled steel sections with an yield stress of 236 Newton per mm square is to be used. Now my permissible bending stress in girders is given by 0.66 multiplied by this yield stress. All right, and in question itself it's given that the yield stress, we have to use the rolled steel sections with a yield stress of how much? This. So my permissible bending stress in the girders is given by 0.66 multiplied by 236 Newton per mm square. So this is equal to, by calculations, it is equal to 155.76 Newton per mm square. All right. But for design purpose, let me take it equal to or let me consider 150 Newton per mm square as the permissible bending stress and girders in my design. All right. So let's find the section modulus. Design moment. How much is our design moment? It is 395 kilonewton meter. For the sake of dimensional homogeneity, since here units are Newton and mm, multiplied by 10 raised power 6 because it was kilonewton meter. Divided by permissible bending stress and girders, how much I am taking? 150 Newton per mm square. So section modulus is by calculations is equal to 2.63 into 10 raised power 6 mm cube. All right. So this is my section modulus, and accordingly I have to select what type of a section I'll be using for my stringer beam. And this is the steel table. This will give us information. How much is my section modulus? It is 2.63 into 10 raised power 6. All right. This is the 2.63. So ISWB 500 will be insufficient. Let's check ISWB 550. ISWB 550 has a section modulus of 2.72 into 10 raised power 6 mm cube. So this will be sufficient and good enough for my stringer beam. So let's take ISWB 550, Indian Standard Wide Flange Beam 550. All right. Let me rub it first. All right. So let's use Indian Standard Wide Flange Beam ISWB 550 for my stringer beams, and which has a section modulus of ZXX along the XX axis. How much? 2723.9 centimeter cube. So that is equal to section modulus along the XX axis for Indian Standard Wide Flange Beam 550 is equal to, according to steel table, 2.72 into 10 raised power 6 mm cube. How much was the requirement for my section modulus? It was 2.63 into 10 raised power 6. I have used 2.72 into 10 raised power 6. That is my section modulus for my Indian Standard Wide Flange Beam 550. So that is good enough for my stringer beams that I am designing. All right. Now let's calculate some of the parameters of the same beam. We need thickness of web. Thickness of web, that is TW. That for my ISWB 550 is how much? This is the thickness of web. ISWB 550 over here. How much is the thickness of web? 10.5 mm. 10.5 mm. And depth of section is in the nomenclature itself. This denotes depth of section. Depth of section for my Indian Standard Wide Flange Beam 550 is 550 mm. All right. After that, I have to calculate the shear stresses. Shear stresses, and we have to check whether the section we have used is safe to bear our shear stress or not. All right. Since we have calculated that it will be good enough to handle or withstand my moment. Why? Because section modulus is equal to moment by the permissible bending stress, and I already calculated the section modulus required for my moment, and that came equivalent to 2.63. Then I propose that I'll be using ISWB 550, which has a section modulus of 2.72. Okay, all right, done. This will sustain our moment that is gonna come, all right. But let's check. How about the shear forces? For that, we have to check the shear stresses. The shear stresses are given by shear stress is equal to shear force divided by H, depth of section, multiplied by the thickness of the web. All right, let me write it over here. Shear stress is given by, so shear stress is given by shear force. How much is our design shear force? It is 316 kilonewton for dimensional homogeneity into 10 raised power 3 divided by how much is the depth of the section? 550 mm. And how much is the thickness of the web for our ISWB 550? From the steel table, we saw it was equal to 10.5 mm. So the shear stresses will be equal to, by calculations, 54.71 Newton per mm square. All right. And the shear stresses, it should be less than, or the parameter that is to be checked is that it should be less than 0.4 into Fi. Fi is my yield stress. How much was that? It was 236 Newton per mm square. That's given in the section, question itself, that you have to use rolled steel sections which have yield stress of 236 Newton per mm square. So by calculations, it is, this thing is equal to 94.4 Newton per mm square. So the maximum shear stresses it can bear is equal to 94.4 Newton per mm square. That is in the material property itself. It is given equal to 0.4 multiplied by the Fi. Fi is our the yield stress, and we are using the rolled steel sections with a yield stress of 236 Newton per mm square that have the capability of absorbing 0.4 times the shear stresses, and for these sections it has the capability of absorbing shear stress equal to how much? 94.4 Newton per mm square. But how much is coming on it? 54.71 Newton per mm square. So our section is safe because 54.71 is less than 94.4 Newton per mm square, hence safe. So the section that I chose for my stringer beams as ISWB 550 is safe for my moment, obviously, because I have chosen it on the basis of moment itself, and it can handle my shear force as well. Moving on, let's design the cross girders, hence safe. All right, let us design the cross girders. So I'll be using ISWB, that is known as Indian Standard Wide Flange Beam 550, as my stringer beams for the steel truss bridge that we are designing. All right. Design of cross girders. Design of cross girders. All right. First, let us calculate the span of the cross girder. Span of the cross girder. How much is the span of the cross girder? It is one, let me show you in the diagram. You can see in the cross section of the deck itself, how much is the span of the cross girder. See, this is the cross girder. In the cross section, you can see it is here. These are the stringer beams. These are placed 1.875 meters apart. After that, we have our curved stone, which is 0.6 meters, 0.6 meters. So how much will be the span of the cross girders? It is equal to 1.875 into 4 plus twice 0.6. The span of the cross girder is equal to 1.875 multiplied by 4 plus twice 0.6. All right, so it is 0.6 plus 1.875 plus 1.875 plus 1.875 plus 1.875 plus 0.6. This is the span of my cross girder. All right, in the cross section of deck you can see. So how much is it? By calculations, it is equal to 8.7 meters. So the span of my cross girder is 8.7 meters. After that, I have to calculate the dead load due to the slab and the wearing coat or the wearing course. Dead load due to slab and wearing coat is equal to, how much was the dead weight of slab and wearing coat? It is 7 kilonewton per meter square. We have already calculated it. Now dead load due to slab and the wearing coat on my cross girders is 7 multiplied by 5. All right, so it is 35 kilonewton per meter. All right, In the question itself, we assumed that we'll be providing cross girders are provided at 5-meter intervals joining the nodal points. Please recall the discussions. Cross girders are provided at 5-meter intervals joining the nodal points. Cross girders are provided at 5-meter intervals joining the nodal points. So dead load due to slab and wearing coat is equal to 7 multiplied by 5, that is 35 kilonewton per meter. After that, we have to calculate the dead load due to stringer beams. All right. In addition to the slab and the wearing coat, dead load due to stringer beams is also going to come on the cross girders. So dead load due to stringer beams is how much? See, while designing stringer beam, we assume that the dead load due to stringer beam or the self weight of the stringer beam is 1 kilonewton per meter. All right, we just assume that, and at that point we didn't know that what section we are proposing for the stringer beam. That's why we assumed it to be 1 kilonewton per meter. But this time we don't have any need to assume. Why? Because we know what type of stringer beam did we use. We used ISWB 550. All right, so we know its area of stringer beam. This will be given by our steel table. All right, ISWB 550, it has an area of 143.34 centimeters square. All right, so the area of the stringer beam is 143.34 centimeters square, and we also know that the density for the steel is how much? 78.5 kilonewton per cubic meter. I know the area of my stringer beam from the steel table because I know my stringer beam is ISWB 550. So area of the stringer beam is given as 143.34 centimeter cube, and density for steel, we know that it's equal to 78.5 kilonewton per cubic meter. Then the weight of the stringer beam will be equal to, weight is equal to area multiplied by the density. How much is area? 143.34 for dimensional homogeneity, because here it's meter, 10 raised by minus 4. Density 78.5 kilonewton per cubic meter. By calculations, weight of the stringer beam or dead load of the stringer beam is 1.125 kilonewton per meter. All right, I'm once again repeating it that while we were designing our stringer beams, we assumed its dead load to be 1 kilonewton per meter, because at that time we didn't know what section we are using. So that time we assumed it. All right, but this time there is no need for assumptions, because we know that the dead load due to stringer beam is ISWB 550. We know its area, we know density of steel, so I have calculated its weight. So its dead weight is 1.125 kilonewton per meter. All right, moving on. After that, so this is weight of the stringer. We have to calculate how many we have, or at what spacing we have. We have at every 5. All right, so I'll multiply it by that. So dead load due to stringer beams is equal to how much? 1.125 kilonewton per meter multiplied by 5. All right, because we are designing our cross girder, and by calculations it is equal to 5.625 kilonewton. All right, now I have calculated the span of my cross girder. I have calculated dead load due to slab and the wearing coat. So I have calculated the dead load due to the stringer beams. All right, after that, to stringer beams I'll be adding something more. add load due to connectors. They will be my bolts or welds or the rivets by which I am connecting my sections. So to the dead load of stringer beams, in addition to its dead load, I have to also add the load due to connectors, which may be bolts, welds or the rivets. And since it is 5.625, let's approximate it to 6 kilonewton. So I'll be approximating the load due to connectors to be equal to 0.375 kilonewton. Alright, so that the total dead load due to stringer beams, including the load due to connectors, will be equal to how much? 6 kilonewton. This plus this. Alright, moving on. After that, self weight of the cross girder. Self weight of cross girder. Self weight of cross girder is given by 0.2 L plus 1 kilonewton per meter. This is the general design considerations for the design of the plate girders. Please recall the discussions wherein I, in the very beginning, told you that we design these cross girders as plate girders, and the general design consideration for designing plate girders is that we take its self weight equal to 0.2 L plus 1, where L is the span. All right, so it will be equal to 0.2. How much is L? We calculated the span of the cross girders to be equal to 8.7 meters. All right, so this will be 0.2 multiplied by 8.7, all right, plus 1. So by calculations, this is equal to 2.74 kilonewton per meter, which I'll be approximating for my design calculations to be equal to 3 kilonewton per meter. All right, now the total uniformly distributed load on the cross girder is equal to total uniformly distributed load is equal to how much? It is equal to, it was dead load due to slab and wearing core, that was 35 kilonewton per meter. Then its self weight, that is 3. So it is equal to 38 kilonewton per meter. All right. So let me draw the diagram for the dead load concentrations of the cross girders that I'm designing for my steel truss bridge. All right, this is my cross girder. What is the span? Span is 8.7 meters. All right, then we have a uniformly distributed load that is due to self weight of the slab and the wearing coat, all right, and the self weight of the cross girder itself, which we calculated to be equal to 38 kilonewton per meter. After that, dead load due to stringer beams, including the connectors, that we calculated is equal to 6 kilonewton. This is the curb stone, 0.6, because cross girders are along the cross section. So 0.6 curb stone, total length or total span 8.7 meters. Uniformly distributed load due to its self weight and due to the self weight of the slab and the wearing coat, 38 kilonewton per meter. Then dead load due to stringer beams which are placed 1.875 meters apart. First one will be here, it is 6 kilonewton. Then after 1.875 meters, 6, here 6, then 6, then 6. All right, this is 1.875, all right, meters. Then we have 1.875 meters, Then we have 1.875 meters, and then again 1.875 meters. Then the curbstone 0.6. This is the cross section of the deck. This is the cross girder. This is the cross girder. 8.7 meter is the span, and this is the loading condition on the cross girder, which is a simply supported beam as well, just like stringer beam. And this is the loading condition due to the dead load. Dead load due to the stringer beams, including connectors, and dead load due to its self-weight and due to self-weight of the slab and the bearing core. Now we have to calculate the dead load, maximum moment, and maximum shear force. Then we'll see the live load conditions according to IRC Class A track vehicle, and then we'll calculate the moment, maximum moment, and the shear force according to the live load conditions, and we'll be summating the two. That will be our design moment and design shear force after the application, or after applying the impact factors on live load, moment, and shear. All right,